Kriging with external drift. Data analysis and interpolation.
This is the fourth geostatistic course about Kriging and co-Kriging interpolation and mapping. As a part of this fourth geostatistic course, you have already available the following lessons: ordinary Kriging, universal Kriging, regression Kriging, and now we are working on the Kriging with external drift. The previous lesson was an introduction of the Kriging with external drift and also how to create a grid using only QGIS for this particular type of Kriging interpolation. And today we are going to work on the second part. In this second part, we are going to explore the data using some scripts that we created at the previous lessons. We are going to analyze the variable that we are going to use to interpolate, in this case the zinc concentration, and also we are going to analyze the variable that we are going to use as an external drift. Then we are going to see what is the best model that we can fit in our data set in order to perform a proper Kriging with external drift. Later, we are going to work on the interpolation with RStudio, and at the end, we are going to import the results that we get in RStudio to QGIS. In this case, we are going to perform two types of Kriging. One is going to be the Kriging with external drift, and the other one is going to be the ordinary Kriging. And then we are going to compare both of them to see what is providing the best results. If you would like to have full access to all the lessons, just go to the Geo RGB community website at giscourse.online, select the fourth geostatistic course, then enroll and you will be ready to start learning. Here, as you can see, we have several lessons. The lesson 0 is the introduction. The lesson 1 is the ordinary Kriging with more than 2 hours 30 minutes of content. The lesson 2 is about universal Kriging with 4 hours 30 minutes of content. The lesson 3 is about regression Kriging. In this lesson we have several parts, and in total is more than 9 hours 30 minutes of content. And now we are on the fourth lesson. Here, as you can see, we have two parts. The first part is just an introduction about Kriging with external drift and also how to create a grid using only QGIS. And the second part is the video for today. And in this case, we are going to do the data analysis and also the interpolation. If you don't want to get enrolled in our website, you can follow us in YouTube. We are loading also all the content here, but in YouTube there are some restrictions. But if you are interested in this kind of material, you can also follow the lessons through YouTube. Remember that at the website you can download all the scripts that we are using during the lessons. In the previous tutorial, we created this grid using only QGIS. Now what we want to do is to predict the zinc concentrations in those unsampled locations. These unsampled locations are representing for each of these squares in our grid. Then we have the sampling locations indicating with the red dots, and also the unsampled locations, that is each of these squares. And we are going to predict the values of the zinc concentration in the unsampled locations using the technique Kriging with external drift. The first thing I would like to do is the analysis of the variable that is going to be interpolated. In this case is the zinc concentration. Then to do that one, we are going to use an R script that is going to be the number 6, histogram convince. And remember that this script was created at the lesson 5 of the first geostatistic course. Then double click to open. Let's go to fill the information. Here what we want is the Muse dataset. The parameter of interest is the zinc concentration. Label X is going to be the zinc concentration in ppms. Label Y is going to be the number of samples. Title of the graph is going to be histogram. Subtitle in this case is going to be raw data because we are going to apply the histogram without any type of transformation. The minimum value and the maximum value, we are going to get that one from the attribute table of the Muse data set. For the zinc concentration, the minimum is 113 and the maximum is 1839. Then we can add these values here. And the interval is going to be calculated with the calculator. The interval is going to be how width is going to be each bin. Then first we have to know how many bins we need. The number of bins, we are going to calculate that one with the total number of samples, that is 155, and we are going to do the root square. In this case is 12.5, that is going to be around 12 bins. That is going to be good. Then in order to know how width is going to be each bin, we have to do the difference between the maximum and the minimum value in order to have an interval. Then it's going to be 8,839 less 113, and this value is going to be divided by the total number of bins. In this case is 12. Now with this value we have the interval for each bin. Now let's go to copy this value here, Ctrl C, and let's go to page over here, Ctrl V, and now we can run this one. Double click to open. We can make this screen bigger. And as you can see, the majority of the samples are located in this area of the graph. The graph is totally asymmetric, and here we have 65 samples, here we have 22, and in this area of the graph we don't have too much samples. Now we can create a different histogram also with the box plot to see other parameters associated with this data set. This new script is the number 13, and we created this script at the 6th lesson of the first geostatistic course. Is this one over here? Double click again. Let's go to select the Muse data set. The parameter is going to be the zinc concentration. The label X is going to be the zinc concentration in ppm. Label Y is going to be the number of samples. Title of the graph is going to be histogram plus box plot. Subtitle is going to be raw data, and the parameters is going to be the same as we did before. I'm going to add all this information. I already added all the information, and now we are ready to run this script. Double click to open. Let's go to make the screen bigger. As you can see, this histogram is the same as the one we created previously, right? But in this one, we have an extra information. We have the mean value with the red line, and we have the median with the black dash line. Also here at the bottom, we have the box plot. And with the box plot, also we have the outliers over here. Then in this histogram, what we can see is that we have a big skewness to the left. Also that the mean value and the median value, they are pretty separated. And in this case, the mean value is not representing all the data, because most of the samples are located over here and we have the mean value over here. Then in this case, the mean value is not representing all the data set, and that's very important. And the problem here is, as we have these outliers here that has a big concentration of zinc, these values are pushing the mean value to this area over here. Also, as you can see, the box of the box plot is to the left, indicating asymmetry on the data set. At the end, what we want for the variable that is going to be interpolated, that is going to be the zinc concentration, is to have a normal distribution. If we have a normal distribution, the outliers, if there is outliers in our data set, are going to be symmetric. Also, the mean value and the median, they are going to be close, and they are going to be located in the area of the graph where we have more samples, and then that values are going to be representative of our data. Remember that the mean value is an average of all the samples, and the same happens with the semi-variogram. It's an average between the pair of samples according to the distance. Then if this average, if the mean value that is an average, it's not representative of all the data, then in this case, when we are doing the semi-variogram, we are not going to have good results also, because the data is not normally distributed, right? I'm not saying that has to be 100% normally distributed. It has to be as closer as possible to the normal distribution, because the semi-variogram is not a parametric function. Then we can work with data that is not normally distributed. But as close as to the normal distribution, better is going to be the results associated with the semi-variogram. Then, in order to have a distribution that is going to be more close to the normal distribution, what we are going to do is transform the zinc concentration. We are going to use the log with base 10 to do the transformation. And we can create the same graph, but instead to use the zinc concentration, what we are going to use is the log 10 of the zinc concentration, okay? And we are going to do the same graph, but now we have to change these parameters over here in order to have a proper graph. But we are going to do the same, right? We can go to the attribute table, go to the log 10 for the zinc concentration. Remember that this parameter was created at the previous lesson, and that's it, okay? Now I'm going to show you the graph, because I did it already, and I have the graph over here. The two first graphs are related with the raw data. We was talking already about these two graphs, and now we have the same graph, but with the log 10 transformation. As you can see, the data is not perfectly normally distributed, but the distribution is more close to the normality, right? And if we compare this graph with this graph, it is clear that there is a big improvement of the distribution of the data. Also, when we check, for example, the box plot, we can see that the box now is more close to the middle. Also, the mean and the median value, they are closer. And also, in this case, we already removed the outliers. All these things are pretty indicative of the normal distribution of our data. In this case, the goal of doing the log 10 transformation is double. In one hand, because we want to have the zinc concentration in a normal distribution to get a proper semi-variogram, but remember that in this case, we are not going to use the zinc concentration to do the semi-variogram, because we are going to work with the residuals of the zinc concentration. And these residuals from the zinc concentration, they are coming from the model that is ordinary least squares, right? But if the original data, that in this case is the zinc concentration, it is already normally distributed, the results that we are going to get for the residuals are going to be also better, right? And that's one of our objectives. The other objective is that the variable of being interpolated, that is the zinc concentration, and the variable that we are going to use as external drift, that is going to be the distance to the river, has to show a linear relation. Remember that if we want to apply for Kriging with external drift, the relation between the variable being interpolated and the external drift has to be a linear one. And as we are going to see later, if we don't apply any transformation to the zinc concentration, it is going to be really hard to have a linear relation between these two variables. And that's the next thing that we are going to see now. First thing is to add a new variable in our data set. Then go to the Muse data set, open the attribute table, open the edition, go to the field calculator, and this new variable is going to be the square root of the distance to the river. Square root distance to river. In this case, it's going to be a decimal number. This precision is good. Then we are going to open the math. we are going to select the square root, then go to the values and fields, field and values, select the distance to the river, then we can run this one. Let me close this one here. Okay, and now we have a new field here that is the square root of the distance to the river with 3 decimals. Now we can close this one, save, and now we can close the attribute table. I would like to do a visual analysis of the relation between the zinc concentration and the distance to the river. To do that one, we are going to use the script number 19, that it comes from the first lesson of the second geostatistic course, and it is this script over here, scatter plot. Then here we are going to select the Muse data set. For the X, we are going to add the distance to the river. For the Y, the zinc concentration. That's what we are going to add to the labels. Title of the graph is going to be a scatter plot, and subtitle is going to be raw data. I'm going to add all this information. I already put all the labels, and now I'm ready to run. Double click to open. Let's go to make this screen bigger. Here we didn't make any transformation on the zinc concentration. That's the original values in part per millions, and also here we have the distance to the river Muse in meters. Okay, and as we can see, there is a relation between these two variables, because as closer we are to the river, higher is the zinc concentration, as you can see in all these values. But as you can see, the relation is not linear. It's doing this very curve like an L, as you can see. And this kind of relation, it is clear that is not linear. Then we have to try to make some transformations here in order to see if we can get a linear relation between these two variables. Now we are going to create the same graph, but we are going to use the log 10 for the zinc concentration. Then go to QGIS here. Here at the zinc concentration, we are going to change for the log 10 zinc concentration. Here at the label, we are going to add log 10. And here for the subtitle, we are going to put transform data. Now we can run this new graph to see what's going on. Double click to open, and let's go to make this screen bigger. And as you can see, now there is an improvement if we compare with the previous one. As you can see here, the data is very accumulated in this area, making this kind of L. But here is more lax, right? Here it starts to show a linear relation between the two variables, but still having here a kind of curve for the data. That is indicating that maybe it is not a perfect linear relation. Then we have to apply more modifications. The next thing that we can do, for example, is log 10 for the zinc concentration and also the log 10 for the distance to the river. And the next one is going to be the log 10 for the zinc concentration and the square root for the distance to the river. But I'm not going to do that one. I'm going to show you the graph, but you can do that one just changing the parameters here, right? Here you can put the distance to the river as a log 10, is this variable here, we already calculated, and also we can do a same graph but with the square root to the distance to the river. I already did, and I have the graph already here. Then, as we said previously, this one is not showing a linear relation. This one starts to show something, but it's still a curve over here. But when we apply the log 10 for the zinc concentration and the log 10 for the distance to the river, we can see that now it is showing a linear relation, right? And that linear relation is even more clear when we are using the log 10 for the zinc concentration and the square root for the distance to the river. Here it is more clear. But also we can fit here a model in order to have more clear what is the best model for our data, and that's what we are going to do now. Now we can go deeper in the analysis of the model that we have to use for Kriging with external drift with the scripts number 31 and 32 that comes from the fourth lesson of the second geostatistic course. First, let's go to analyze the worst case scenario with the script number 31, that is Polynomial Regression Fit. Then select the Muse dataset. In X, we are going to have the distance to the river. Y is going to be the zinc concentration. Label X is going to be the same as this one. Then I'm going to copy and paste. For the label Y is going to be the same. But in this case, it's just the zinc concentration. Title of the graph, we can add this information here. Polynomial regression fitting. And subtitle is going to be raw data. Then we can run this one and double click to see the results. Now we can make this one bigger. And as you can see, it's pretty clear that any of these models fit really well on the data, right? Here we have the regression type that is linear, that is the second order polynomial, and also the third order polynomial. And no one of these ones fit really well on the data, indicating that in this case, the data is not showing a linear relation, right? In this case, we are working with the zinc concentration and the distance to the river. There is no transformation in any of these two variables. Now we are going to see what happened with the other scenarios, but I already created the graphs in order to save some time in the video. But also, if you want to go deeper in the understanding of all these models, you can check the fourth lesson of the second geostatistics course, because we have already talked about these models and how you can analyze the information of these models in that video tutorial. Now we can see the graphs here with different results. And as you can see, when we have zinc concentration and distance to the river in meters, the model doesn't fit well, right? When we change here to the log 10 for the zinc concentration, and here we left the distance to the river without any modification, you can see that still the data is not fitting really well, right? When these things happen, it is going to be reflective on the residuals. We are not going to get good residuals with these models, okay? And that's something really important, because if we don't have good residuals, the model is not good. Then we cannot use that model to do the Kriging with external drift. Then it is really important to select the proper variables to fit the model, okay? In the third case, where we are using the log 10 for the zinc concentration and the log 10 for the distance to the river, we can see that now the relation is pretty linear, right? But here we have a lot of dots. But in this area of the graph, we have to take the model that divide the data set, right? And we want to have the data set divided pretty equal in both sides of the model, right? And this one, it is not that bad, but it's not the best, right? When we check the log 10 for the zinc concentration and the square root for the distance to the river, we can see that this one is the best model, because, you know, even for any of the regressions, the first order, the second order, and the third order, they are pretty similar, right? It is indicating that in this case, the relation is pretty linear, and it's a model that is really good to work with ordinary less squares. And that's the goal in this case. Here we did a graphical analysis of our model, but also we can use a quantitative analysis using the next script, right? This one here, regression, residuals, errors. Then here we are going to select the Muse data set. Here the variable of interest, that for the X is going to be, for example, the log 10 for the distance to the river, and for the Y is going to be the log 10 for the zinc concentration. Then what we are going to do now is to analyze quantitative this model over here, and we are going to compare this model with this model, quantitative, okay? Then the first one, let's go to run, and let's go to make this one bigger. And here we have the different results for the different degrees of the polynomial, right? This one is for the first degree when the model is a linear one. Here we have the statistics for the residuals, the minimum value, the maximum value, the first quantile, the third quantile, and the median. It is supposed that when we are using the ordinary least squares, the mean is going to be 0. Then we can see here that the variable that we are using, that in this case is the distance to the river, is significative. Also, we can see that we have this residual standard error and this R square. This R square is indicating that there is relation between the two variables. Okay, it's almost 0.6. And also the model has this p-value indicating that we have a valid model. Now we can do the same but using the other model. Then in this case, Muse River dataset, we are going to select for the X the square root distance to the river, and for the Y the log 10 for the zinc concentration. Then we can run this one, and let's go to make this screen bigger, and let's go to compare with the linear model, that is the first one, this model over here. In this case, we have the same information. We have the formula that we are using. We have the statistics for the residuals. We have that the distance to the river, in this case is the square root, right, is significative. In this case, the standard error is smaller than in the other case. In the other case, it was 0.201, but in this case, the error is 0.1988. It is pretty close, but it's a little bit less. And also the relation, the R square in this second model is bigger, indicating a bigger relation between the two variables. The differences is not really big, but it's a little bit higher the value over here, right? And also again, we have a model that is valid. Now we can compare also for a second and a third degree, but it doesn't worth it, right? Because why we want to complicate our model if we can make the same results with a simple model, right? Here, for example, why you want to use the second or the third model when with a first order polynomial you have results that are good, right? It doesn't worth it. Now that we know that we are going to use this model for the Kriging with external drift, we have to add this variable, square root distance to the river, to our grid. And also remember that when we are doing Kriging with external drift, the external drift, that in this case is the distance to the river, need to have an influence on the interpolated variable, that is going to be the zinc concentration. And in this case, there is a clear relation, right? As we said previously, as closer we are to the river, higher is the zinc concentration. And the reason of that is because the river is the mechanism for transporting the sediments that are rich in zinc. And these sediments are going to be deposited in the flooded areas. And these areas are close to the river. Then let's go to add the new variable to the grid. We can close all these ones. Select the grid. Muse grid. Open the attribute table, select the pencil to edit this table, go to the field calculator, new field is going to be the square root, the distance to the river. Then here, decimal number, this one is good, we want the math, the square root, this one, and here we want to select the distance to the river. That is going to be this variable over here. And now we can run these ones. Okay. And now the new field has been added. Then close the pencil, save, and close. And now we are ready to export the Muse dataset and also the Muse grid to RStudio, and then do the interpolation with Kriging with external div with R. Let's go to export first the dataset, then go to export, save feature as, select here this format, CSV, then select the location where you want to save the file. It's going to be, I created already a folder, Kriging with external drift part 2, dataset, Muse data. Save. And the rest of things are okay. And okay. And also now I'm going to do the same for the Muse grid. Then export feature as. This format is the one we want. And here is going to be Muse grid. Save and OK. Now we can start analysis with RStudio.
The Geo RGB community is a place where science is paramount. Our mission is to provide you with engaging, insightful video tutorials that exceed expectations. Did you find this tutorial to be both interesting and informative? Do you think it will assist you in your projects? Do you believe it could be useful for others too? Let's join forces to disseminate the information and make it available to all. Your support can aid in the growth of the Geo RGB community, allowing us to provide higher quality and more innovative video tutorials and services. If you enjoyed the content, please consider subscribing, liking, and leaving a comment. Your feedback is greatly appreciated. Remember, together, we all make up the Geo RGB community. We all play on the same team, Geo RGB.
Then we can load these two libraries. This one is to work with spatial data, and this one is to create the Kriging, the semivariograms. First, we are going to load the grid that we created. Here, I specify the location of this grid. This one over here is this link over here, right? If I copy this one and I added the Muse grid, that's the same information that you can see in this line over here. Then we can load the grid. And remember that the grid is a data frame. I put this name, grid QGIS. Then if we click over here, we are going to see this data set. What we have in this data set, the ID number, the X and Y coordinates, the distance to the river, and the square root distance to the river, for a total of 3,153 different points, okay? That's our unsampling locations. Now we can move on to the next one. In the next one, we are going to add a spatial structure to our grid, okay? Here also I have a tabs related with the original Muse data set and the original Muse grid, okay, as we saw on the first part of this lesson. But we are going to work with the one that we created, okay? Then here I'm going to run this one. I'm going to say that the X and Y coordinates in this data frame are coordinates. Then now we have a spatial point data frame. We don't have longer a data frame. Then we are going to add topology to this data frame. Now we can plot the new grid. Is this one? What we can see here is just the ID number, okay? Also with the SP plot, we can see what information we have in this grid, right? And we have these three things. We have the ID, we have the distance to the river, and we have the square root distance to the river. As this legend is providing very high numbers, over here we cannot see the distance to the river well here, right? Then what we can do is just to do the SP plot, but just I want to see the graph number 3, that is the one of my interest, right? Is this one. Then we can run this line here just to see this graph. The next thing is to load the data set that we created with QGIS with the samples. Also, we are going to add a spatial structure to this data set. But first, let's go to check the data set. Is this one. And what we have here is again the ID number, the X and Y coordinates, the different metal concentrations. But for us, the interesting thing is the log 10 with the zinc concentration and the square root distance to the river. Then let's go to run the next script. And now we are going to create the model. Remember that this model is just a simple linear model where we are saying that the log 10 for the zinc concentration is depending on the square root distance to the river. Then we assign this name to the model, Kriging with external drift, linear model, and these variables are located in this data set, and we are using a linear model. Then we can run this one and see the summary. This summary is the same as we saw when we was doing the analysis in QGIS, right? Here we have the standard error, and here we have the R square. It is important to indicate that when we are using these variables, we are not doing any transformation with R, because we have already these variables transformed in our data set. I don't know if now we can see the data set because, oh yeah, we can see. We have the variables in our data set. We are not making any transformation with R. We have the variables already here, and we are using these variables to do all the things, right? Even here is saying log 10. We are not applying any log 10 to the zinc, okay? Because we have already the variable in the data set, okay? Don't be confusing with this one, also for the square root, okay? Then the next thing is to create the semi-variogram of the residuals, okay? Use the same variables as the model. It is really important. This script is to create the variogram, okay? And as you can see, we are using the same variables as we have here at the model, okay? And the data set is the same. To do the semi-variogram, it is important to have the data set as a spatial point data frame, okay? As we did over here with this line over here. Then we can run this one. And now we can plot the semi-variogram. We are saying that we want to plot this model. Is the model that we created here that is equal to all this one. And also we want to see the number of pair of samples for each lag. And it's this one. Remember that here we have the distance, and here we have the semi-variance for the log 10 of the zinc concentration, but it's for the residuals, okay? Those values are for the residuals. The software automatically take the deterministic model and provide us just the residuals in this case, okay? An important thing here is that we can see that there is a structure on the residuals, okay? There is a spatial autocorrelation on the residuals. And now we can move on to the next one. We get a general view here, and now we can be focused on the correlated area. Remember that the correlated area is this area over here. We are not interested in this one, right? Then in order to make this graph smaller and just be focused in this area, we are going to add this information over here, that we want the cutoff until 1200, that is going to be approximately until here, and we want 1 lag every 100 meters. Then this script and this script are the same, right? The only thing is changing in this one is that I added the cutoff and the width. Then, as I said here, focusing on the correlated area. Then we can run these 2 lines, and also now we can plot. Now, as you can see, that one is shorter because now it gets until 1200. Before, it was until 1600, but we are not interested in all this data because that one is uncorrelated. It is not spatially correlated, right? The correlated area is this one over here. Now we are going to fit a model on our data, and with this script, the software is going to provide automatically what is the best model from these 5 different models. Then we can run this one, and according to the software, the best model is this one. What is this model? It's a spherical model that has this Niagara effect, that has this partial seal. Remember that the seal is this one plus this one, and also has this range of this amount. In this case, I decided to the software to give me this information, but you can fit the model manually, okay? There are different options. All these options were explained at the 5th lesson of the 3rd geostatistics course. Then if you want to know more about all this stuff, my recommendation is just to watch that video tutorial. Remember that this model has been fitting on this data according to the weighted least squares, and it provides the minimum residuals, okay? Don't be confused with these residuals from this model, that the residuals that we get from the linear model, okay? They are different things, okay? And sometimes, for example, you cannot trust with the automatic fit because maybe you don't want to use this lag over here, because maybe this lag has just a very few pair of samples and you are not interested to use this lag for fitting the model on this data, and then you can fit that one manually, okay? Sometimes the automatic fit is not the best, right? But in this case, is good for my necessities, right? Then with the next script, we are going to say that we want that model, and then we are going to provide here the approximately values that we get over here, okay, to fit the model on the data. Then we are using this script. Then we are providing the variogram that we created, is this variogram over here, and the parameters associated with the model that we want to fit on the data. Then we can run this line over here, and in order to plot the model on the data, we can use the next script. We added here the semi-variogram, and we added here the model, and also we want to see the numbers associated with the pair of samples for each lag, right? Then we can run this one, and now we have the model fit on the data. At this point, if you apply for a different type of models and you want to know what is the best fit on your data, you also can do the cross-validation. Remember that we did a full lesson about cross-validation, and that video tutorial comes from the lesson 8 of the 3rd geostatistics course. Then if you are interested in cross-validation, I recommend to watch that video tutorial. Then we have 2 different models, right? One is this model, that is for the residuals of the zinc concentration, and we have the other model that it was this model over here with the first order, that is related with the deterministic model, okay? There are 2 different things, okay? Don't be confused. One model is for the Kriging interpolation, and the other model, that is this model, is for getting the residuals to apply the Kriging, okay? Then they are different things. Now with the next script, what we are going to do is the interpolation. Then we are going to assign this name to the new object. We are using the Kriging script, and here again, if you see, what we are adding here is the same variables that we decided for our model. Remember that our linear model is this one, and we have these two variables, and that's the variables that we want to add over here. Also, we are adding the data set and the grid that we created, and also the model that we want to use. This model is the same as this one. Then now we can run this one and see the summary. One important thing is that when we are running the Kriging script, it provides using universal Kriging. But remember that we are going to use the term universal Kriging when the predictors are the coordinates, okay? But in this case, the predictor is another variable that is not the coordinates. That in this case, what we are going to say is using Kriging with external drift, right? That's just something that I want to mention. Then with the summary, we can see the information associated with the grid, right? We can see the maximum and minimum values for the grid, for the coordinates. We can see coordinate reference systems if we added any coordinate reference systems, the total number of predictions that we have, the dimension of the cells, and also how many cells we have, and also the variables that we have inside this grid. And as you can see in this grid, we have two variables, the predictions and also the variance. Now with the next script using the sp-plot, we can plot the prediction map using this variable. This variable is the first variable that we have in our grid. Then we are going to select this ramp of colors, and we are going to add this title to the graph, predictions based on Kriging with external drift. Then what we need to add here, we need to add the Kriging with external drift interpolation that we created here at the top. Then we can run this one first. We can see the graph over here. That's for the predictions. And now we can see also the map for the variance. The only difference here is that we have to add the new variable, that is the variance. Then we can run this one and also see the graph. For this one, we added a different ramp of colors. As you can see, where we have samples is where we are going to have the minimum error, and where we don't have any samples is where we are going to have the biggest variance of the data. The next step is to create a raster file with the prediction map in order to be open or to be exported to QGIS. And in QGIS, we can make the final edition of the map. Then we are going to run this one. We are going to load the raster library. Then we are going to call this object with this name, and we are going to convert this interpolation, this map interpolation, that is this one, in a raster file with this script. We can run, and now we can plot the results. If you want to see the full results, you can remove these ones and run the script again. Now with this one, we can see where the file is going to be saved, right? Because that's the link where we are going to save all the information in this project. And that one is okay. Then I can run the next line. That is to create the raster file. I'm going to create a raster file that is this object. That object is this one over here, and I want to add with this name. I don't want to have any new value. Override is true. Then with the next line, we can see the files inside that folder, inside this folder. Then we have this one, and this one. This one is the one that we created. Now, if we go to the folder, that is going to be this one, is this one, is this one over here. Now we can open this one with QGIS. Then go here, add a layer, it's a raster file. Go here, select the folder, here, Kriging with external div, interpolation, open, add, and close. Then we can add the reference coordinate systems, that is going to be the same as this one, 28992. 28992 is this one, okay. And also now we can edit this map. But before to edit this map, we have to understand that the values that we have in this map is log 10. Then we have to reverse the transformation. In order to reverse the transformation, we are going to go to raster calculator. Here at the raster calculator expressions, we are going to put 10 to the power, where is to the power? This one of this raster file. This raster file is this one over here, is the one that we created. And then we are going to save this one. No, here, let me see, number 4. We can save here with this name, but I am going to add here reverse transformation. In order to have again the values for the zinc concentration in parts per million. Save and OK. And that's the one. We are not interested in this one, we are interested in this one. Then we can edit this layer, select single shadow band color, here linear, equal intervals, and we can select a different ramp. Let me see what we have here. I'm going to add this one, but I'm going to invert the colors. Apply and OK. Maybe here we can select a different one. Stay to linear, exact. No, linear is good, but here we can put quantile. Apply. Maybe this one is better. Or I don't know, maybe the other one is better. Equal intervals. What happens is that we don't have too much values from this concentration to this concentration, right? And that's because the map is very dark. Okay, at the moment, let's go to leave this one. One interesting thing here is that the range goes from 76 to 2149. But if we go to the data set, we are going to see that the range for the zinc concentration goes from 113 to 1839, right? Then it's quite different. In this case, it happens because Kriging, it's sometimes not an exact interpolator, right? We was talking about these things at the lesson 6 of the 4th geostatistic course. Then if you want to learn more about that topic, I recommend just to watch that lesson. Now I would like to compare some of the values that we have at the data set with the values that we get in our raster file. Then I'm going to take this option over here, identify features. Then I'm going to select one feature from the data set, for example this dog over here, and I'm going to see what is the value. Here we have for the zinc concentration 560 ppm, and the value that we have at the pixel is 645. Then we can select another one, for example this one over here. The value that we have in our data set is 1383, but the value that we have in our raster file is 1145. You see that there is some differences, right? Then if we load one plugin, let me show you one thing here, the terrain profile. This one over here, install plugin. Close is this plugin over here, select that one, add this layer, then let's go to select this one, add the layer, and now we can make a profile of our raster file, right? And if we make this profile, for example, from here to here, and as you can see in this case, the zinc concentration is changing a lot, right? As you can see here, we have a value of 1400, but here we have a value of 200. And sometimes when we have these variations from very low concentrations to high concentrations, Kriging is not doing a really good job, right? In order to have a better results, we need to have a lot of samples, right? And at the end, what Kriging is doing is a smooth surface, right? And that's the reason, because the model cannot be pretty adapted to the real values, right? That's the difference that we can see between the data set and also with the raster file. And the reason is because we have high values, right? And then we have low values. And in that case, Kriging is not working really well. Maybe in this case, instead to do a prediction map, it's better to do a simulation map. With the simulation, we can have more realistic results, because at the end, Kriging provides results that are very smooth. Now, I'm curious to know if the ordinary Kriging could provide better results. Then let's go to try and to see what's going on if we apply ordinary Kriging instead to use Kriging with external drift. Let's go to close this one, and let's go to move this one to the center. Now let's go to R, and let's go to work with ordinary Kriging. That is going to be the next line. Then we can run this one. Let's go to create the semi-variogram. But now we are saying that the zinc concentration is constant. We are not saying that it's depending on the distance to the river, as we said previously. And we are using the same data set. Now we can see a general view of the semi-variogram. Again, we are going to select the correlated area. Is this graph. Then now we are going to fit a model automatically. The software provides these values for the model. And as you can see in this case, the partial seal is 0.1 and the Nagar effect is 0.01, okay? It's 10 times smaller. But in this case, with the Kriging with external drift, the Nagar effect is too much bigger compared with the partial seal, right? That is an important thing. Then we are going to create the model. And now we are going to fit the model on the data. We are not going to try any other model. The model that is provided by default for me is good, and we are not going to do then any cross-validation because we are going to use just this model. Now we are going to do the interpolation as we did for external Kriging. Also, let's go to plot the predicted values, and now let's go to plot the variance, and now let's go to export the file, right? That's the file that we are going to export. overwrite, and that's it. Now we can go to the folder, and it's going to be this one over here. Now we can load this file on QGIS as a vector file. Raster is the ordinary Kriging. Interpolation, open, add, close, add the reference coordinate systems, is this one, okay, and now we are going to remove the transformation, okay, because we want to have the concentration in parts per million. Then, as we did before, let's go to raster calculator, 10 to the power of this layer. And now we are going to save this one with this name, but we are going to add here reverse transformation, as we did before for the Kriging with external drift. Reverse transformation. Okay, and save. And okay. Now we are no longer interested in this one, and we are going to work on this one. Let's go to make some modifications here. Single pseudo color. Select a different ramp. I want this one. I want inverse, and I want equal intervals. Apply, and okay. And this one is Kriging, ordinary Kriging, and this one is Kriging with external drift. Now we can see the differences between these two models, right? Also, we can see the range, and here for the range we have from 121 to 1697, and in the other model we have from 76 to 2149. It's a little bit different, right? And on the data set, what we have is from 113 to 1839. Now, in order to see what could be the best model, we can do a cross-validation between these two models. And to do that one, we are going to use the RStudio. With the next script, we are going to use the leave1out cross-validation to evaluate the two models. Then we can run this line. Here, what we are using is this script, create cross-validation. Here we add in the zinc concentration that we are saying that is constant. The location is the data set. The model is the semi-variogram model that we created previously. And here we are doing the same, but for Kriging with external drift. Then we can run this line also now. Now we can see a summary of the residuals from the ordinary Kriging. And also the same for the Kriging with external drift. And now we are going to calculate the root mean square error for the ordinary Kriging and the root mean square error for Kriging with external drift. And as you can see, Kriging with external drift provide a value that is a little bit more smaller, right? But the differences is not that much. This one, it is indicating that the model with Kriging with external drift is a little bit better than the ordinary Kriging. But the differences, again, is not that much and just is based on the root mean square error. If you want to learn more about the leave1out cross-validation technique, I recommend to watch the lesson 8 of the third geostatistics course. Before to finish, I would like to mention something that I forgot to tell you previously, and it is related with the linear model. In this case, as we are using Kriging with external drift, and we fit an ordinary least square model on our data set, then we have to cover some assumptions. We was talking about these assumptions at the third lesson of the fourth geostatistics course related with regression Kriging. And one of that assumptions is that the residual values doesn't have to show any spatial autocorrelation, right? But as you can see in this case, when we was working with the semi-variogram, we saw that the residuals was showing a spatial autocorrelation, right? Then if the residuals are showing a spatial autocorrelation, we have to say that the model is not a good model, then we cannot use that model to do the predictions, right? However, in this particular case, when we are using the Kriging with external drift, let me show you the script here. Is this script. When we are using this script, the Kriging, and we are using the external drift as a variable, this script is going to provide results that are based in generalized least squares, right? Even we fit the model like ordinary least squares, the result that we get at the end after applying the Kriging script is going to be based on generalized least squares. And the generalized least squares is providing the proper structure inside the model in order to have a valid model for the Kriging interpolation. And well, that's it for today. Thank you very much for watching this video and see you on the next lesson.